Aguilar, who is a first-year grad student in the Department of Earth, Atmospheric, and Planetary Sciences. Mariana is actually the creator of this lesson. She wrote the lesson last year to present to a group of middle school students in Medellin, Colombia. And so, Mariana, it's nice to have you here.
Thank you.
And Elena Watson. Elena is a high school teacher from McCutcheon High School, a local high school here in Lafayette. And Elena has been a major part of putting this presentation together, and is the author of one of the documents that we will share with you. I'm going to mention that Mariana has a long-time relationship with Purdue PhysAstro. She was a participant and contributor more recently for the last 6 or so years in our Saturday morning astrophysics at Purdue program. So Mariana has a lot of experience with physics, astronomy, and teacher development and presentations. So Mariana, it's nice to have you.
Thank you.
So we titled the session initially remote sensing, and that may be a little bit misleading because there are other kinds of remote sensing, temperature, weather, and so forth, that are not really related to what we're all about. Our remote sensing is in the context of thinking about landing vehicles, rovers and such, on extraterrestrial surfaces, planets, moons, asteroids. And so in order to do that, we need to know a little bit about the surface. And so our goal today is to show you a method where we can model the process of trying to determine terrain features and possible potential areas to maybe land a physical rover. Either of you two like to add anything to that?
That this is kind of modeling what it would be like as a planetary scientist or an engineer in the future if they were to work for NASA or SpaceX or some company like that. This is kind of the process that the scientists go through that they can try as well.
Okay, so we are actually standing kind of in the area of what will become a planetary terrain. So you see a square on the floor, some hash marks with tape, and we're going to show you how we can utilize this space to get on with our lesson. So with that, shall we start with the PowerPoint?
Yeah.
Okay. All right. Let's move on over to our computers.
I will go ahead and share my screen.
I would also mention, if anybody has a question anytime along the way, please feel free to interrupt us. We are interested in what you want to know that we may not be telling you. And so at any time, just speak up and let us know. Mariana.
Cool. 1 second. So it says I have to put, let's do that.
Hang on.
Okay, I think it's working.
I just added you to be the presenter. See if it goes now.
Okay, try that one. Still not in.
It's not letting you present.
It's open system preferences, grant access and system preferences. But I did that.
Hang on 1 second. In mine, it shows that you have
Your PowerPoint? I might be able to- I think you did try and I didn't get it. Yeah.
Try now. No? That's weird because you're in as a panelist. Sorry, everybody. We're having a little technical difficulty. Give us a second.
Sending it to you yesterday.
Yeah, it says you're the presenter. So yeah, thanks, Kathleen. Yeah, I know this never happens as teachers. The technology always works just fine. Tell you what, exit out, come back in.
Okay.
And when you come back in, I'm gonna leave you as an attendee and I'm just gonna give you rights and see what that does.
Okay. Really doesn't want stuff.
Elena, can you share your screen?
I think so.
Right, just for giggles.
Her.
I don't care, just share anything, just to see. Because maybe it is,
I think I can. I'm in now.
you're back in? Okay,
Yeah.
yeah, you
It's
can.
like this.
Yeah, you are sharing. Okay. Now, Elena, do you have it down at the bottom right now, share?
Mhm.
Okay. And Mariana, do you have it on yours? Does it say share at the bottom? Okay.
The PDF of her presentation, she could do it through that off of mine.
Let's see what happens if I just did it again and let's,
I think it's working now.
hey,
Phew.
we beat technology. Okay.
Okay. Cool. Sorry for the delay. So this is the PowerPoint that we have prepared to kind of give an introduction into this lesson, and this can be used in the classrooms as well. And this is the actual presentation we also used when we presented this in Columbia as well. This is just the mapping planetary terrains lesson. And so we kind of started off by making a sort of interactive way to get the kids interested in planets and space and visiting those bodies in the solar system and beyond. And so we created a pop quiz. And so in the next couple of slides, we show pictures of different celestial bodies in the solar system. And we had the kids, based off each session, each picture in groups, they tried to see what body they thought the picture was from. If it was a planet, a moon, an asteroid, and what the name was, as well as what they think is being shown, what kind of geologic feature. So if it's like a volcano or a desert or anything else like that. And then if they think they could actually land a rover there safely as well. So we had those three main questions for the kids to answer in their groups. And so we started off with this image. And so we let the kids decide and discuss together. And eventually we showed that it was Mars. And that this was a dried up lake that formed within a giant crater. And so we can show them kind of different features of what a geologic feature of like a lake would have looked like back then. and that it was a lake where we've actually landed before with the Perseverance rover that NASA sent a few years ago. And so we had more examples like this. So we had this image, which is just Jupiter, and so we can describe what kind of features this is, and that it wouldn't be safe to land here eventually if we send something. And then just other bodies like this that the kids can kind of learn about that of a moon as well, and then this moon as well too, and then kind of relating that back to real data that's been taken by NASA and real images like the one on the far right of the moon of Saturn. So just a way to get the kids interested. And so then we bring it back all together to talk about as a class to see what they thought of the images, what other, if they were to send a rover, what other data would they like to see besides this, to see where would they like to land, what kind of information is needed. And then moving on, this is just kind of an overview we had of future missions to the moon. Particularly Artemis has been in the news lately for the next mission to send humans to the moon, but other ones that the kids can kind of look into, maybe kind of like an assessment before they start the whole lesson, to kind of start looking at other missions that are going on as well. And this is just another discussion-based question for the students to think about what they actually do need to land a rover, kind of thinking about when they make their planetary surface, what data will they need to collect as well.
Can I pause you for a second?
Yes.
One thing that you said right there that struck me was, you know, when they're talking about these future missions, I think that's a great opportunity for the teachers to have discussions with the kids like, okay, so they have these other missions, and these are clearly very expensive to take, right? So having the kids discuss, why is this important? Why is this that, you know, why would you put that much money towards, what are you gaining? What do you gain if, or what do you lose if you don't? That whole discussion of science being done and really trying to drive it home, like, because eventually they're going to be voters, right?
Yeah.
And they're going to vote for things, and they need to think like, is this what I want? And why do I want this? So being that citizen who has that background of science and understanding as they move forward in life. Does that make sense?
Yeah.
And I think that's good for these kids to have that discussion. Because I mean, one of those missions alone,
Yeah,
millions, right? And okay, so is that what we want to spend money on, or do we spend money on X? And why would we? And those are good discussions to have in a middle school classroom.
I also like to get students' feedback on, for example, this slide. What do you think is needed to land a rover? So we could ask our teachers today the same question.
Sure. So if we want to, could you guys answer in the chat? What do you think is needed to land a rover? Don't be shy.
So what do we want to
Money. Yeah, sure. That's a good one.
I'm thinking specifically about the place where we want to go.
Communication. Communication, remote control of lander, information on conditions, which I think that's pretty important. You mentioned that earlier.
What might we want to know about the terrain where we might want to land a rover? What do we want to know about the terrain? Who's got some ideas?
Well, I mean,
level, rocky.
yeah. Is it level? Is it rocky? I mean, honestly, the biggest thing is if you land it and it's smushy, whatever smushy would be, you know, I'm not thinking just water. I'm thinking just like you land and that just sinks or it just goes down in, you're pretty much done, you know?
Like the picture of Jupiter is like you would get a feature back, but is that feature rocky so you can land on it, or is it clouds so you would go right through it?
Yeah, right.
And if you
See-
spend so many millions of dollars making this and then you get there and it crashes or, yeah.
Yeah.
It's super important.
what happens. Yeah.
Sure.
You can only tell so much from a photograph.
Right,
We need more data.
right.
Okay. Sorry, I didn't mean to interrupt you, but
Great.
Yes.
there's some thoughts.
All right. So just kind of introducing again to the students that they're going to be thinking like actual planetary scientists, engineers, NASA scientists, kind of putting themselves in those shoes as well. And so these are just images from when I and another student from the physics and astronomy department, we kind of set up our own planetary terrain with boxes, which we'll show you how to do as well. And this video link here, if you want to take a look at it, which will send you these slides as well, shows the kind of in-depth process of, which we'll show you today, but if you want to go back to it, the in-depth process of how to do this kind of a lesson. And so the scenario that we gave the kids is that their team in groups that they work in was selected to design a mission to do remote mapping of an extraterrestrial terrain, whether that be a planet or a moon. And so they're going to be having to create a 3D map of the planetary surface. And so they'll be given any equipment they need, and they have to be able to, with the equipment that they have, kind of adapt themselves like NASA engineers and get the data they need with the equipment that they have. And so after they kind of create their map, kind of making them think in that position to what kind of data they will want to get when they land in that location, naming their planet or their moon, and what they want to study, those kinds of things as well. And then we had the kids present their findings as a group as well. But yeah, so that is the general overview. And so then we kind of went into how this lesson works and how it works for other satellites that we send as well to do this kind of real in-depth mission. And so we talk about how when we send satellites to, let's say, like Mars to do the remote sensing, we use radar, which uses electromagnetic waves and pulses of these electromagnetic waves, which are reflected off the actual planetary surface. And then it's sent back to the satellite that's doing the mapping. And so this is used, like I mentioned, for the NASA missions. And then what we're going to be modeling with a similar process is using sonar, which uses the pulses of sound waves reflected off the surface, like our modeled planetary surface, and collected back by the sensor. And so this is used in submarines. And so this is kind of modeled here in the picture to give the kids a better idea of what's happening. So we have the sender on the left-hand side, which is sending that original red wave of the sonar, which is hitting this blue object here and reflecting it back, which is the green lines, which is collected again by the original sender or the receiver. This is kind of the process of what's occurring with radar or sonar. So just to give the kids a bit of a science background on what is actually happening as well. Yes, so I'll move it over to you, Dave.
Okay, I'm going to ask Elena to come up and give me a hand with something here.
Okay, setting up our surface.
Sure. So I'm going to ask Elena to give us a hand here. We approach this, you can assign responsibilities to the students within their team. We also thought it might be cool to create a scenario for having, for setting up like what do I want to say? An original mission where we have a mission engineer. So you could assign students to be, in a student group of 5 or 6. One could be a mission engineer, one could do this and other responsibilities. We also thought it might be cool to actually have somebody, an adult, come in and act as the mission engineer to maybe have a description of, what the mission is, assign responsibilities. There's a lot of flexibility, so I'll leave that up to you all to be creative. What I'm going to have Elena do, we want to show you what you're going to need to do this experiment. So we have the Vernier sensor. This is going to be the basis of our sensing device. We have a meter stick, we have some tape, and I have a metal nut on a string. I'm going to have Elena give me a hand mounting the sensor on the meter stick. A couple of things that you want to keep in mind. We're going to use this basically set up a means of sensing the surface. So there are two things here you want to be a little bit careful of. The on and off button, we don't want to cover that up with tape. There's also an ID number. So your students are going to want to know the ID number when they log into the software. You've got a class with 5 or 6 student groups, and they open the software, and you've got 5 or 6 ID numbers. They need to know which one they are. So, Elena, how about?
One more thing.
Sure.
You also don't want to cover up any of the circle here where the sensor is, because then it will interfere with the distance that it measures. So you want to be sure that circular part there is completely uncovered as well.
Okay, I'm going to hold this part and let you want to do it from the bottom? Like this?
Sure.
Okay.
Okay, move it over.
It'd be a good idea to write down the
Yeah.
ID number, I think, before we do this.
Write it down on a handout or something. This way. Feel secure enough?
Yeah, sure, good. So this is how we will sense the surface. Now, one of the things we want to keep in mind is maintaining a constant distance between the sensor and the floor. So to do that, just going to tie a little weight on a string and slide it onto the meter stick. Now we started initially by taping this on the meter stick, and then discovered that as we move across the surface, we're going to need to adjust where the string is. So rather than tape it in place, we just tie a loop to hold it in place. All right, anything else?
So that, just to clarify, that helps you maintain a constant height between the sensor and the floor.
Yeah, I don't know if you can see the floor, but you will when we do the experiment. This little nut will just touch the floor. So when I move it across the floor, it maintains a constant distance. Okay. We have, should we go ahead and set up the terrain?
Yeah.
Okay, so we have created a square. The dimension can be any dimension you like. We've tried 1 meter square, 1 meter by 2 meters, doesn't really matter. And we're gonna use just some boxes, and if you have whatever shapes, we found when we did this with a class in Columbia, we thought the little boxes would be good. The kids went and got all kinds of other shapes and took boxes and created shapes like craters and slopes and other features that we have maybe overlooked. Anyway, let's try something round. One thing to keep in mind is the scale of the features. Too small, the sensor won't pick up. For example, a box this size may not be picked up by the sensor.
Put it lower, David. I'm down so I can see the ground.
Okay,
There you go. That's better.
all right.
Sorry.
So keep in mind the resolution that the sensor might give. A box like this might be a little small. We can try it and see what happens. Boxes like this are probably pretty good size, pretty good shape. The other thing to keep in mind is the distance between your features. Play around with it, have some fun with your kids, but you may find that the sensor needs a certain amount of distance. We don't know what the wavelength is of the sonar, do we?
Yeah.
And so the wavelength is going to determine the resolution that we're going to get in these features. So it's kind of fun to play around. It can also be a little frustrating until you get exactly what you want.
So
Okay.
I got a question as a
Sure.
middle school science teacher. So doing this the first time, would you limit what they can have so that they get good data, that the data that they get is very usable? Or because if they try to add too many features and that just ends up being just a mess,
Right.
the kids are going to be frustrated at the end. So I guess that's my question.
There's also a lesson in not picking up some of this stuff as well, because that shows that this, as a scientist, you have to think about these kinds of things, and you'd have to get a sensor or a camera or some sort of radar that picks up these kinds of things. So that's also a lesson in itself, but maybe to avoid that kind of conflict, it might be better to just have bigger objects, at least the first time around. Students want to do.
And I like what you said. I mean, yes, I would love for them to have where it doesn't quite make sense, and therefore you can go, okay, why doesn't it? And they have to think through, but maybe the first time so that they actually get data that gives them a decent terrain. And then if they do it again, then maybe then let them have a little bit more freedom and flexibility to play with it. Okay, I'm just thinking,
You could also give,
Stand up so we can see our faces.
oh yeah.
I can do that.
You could also give them a range of objects, objects that have a range of sizes, so that they pick up the larger features. You know, they're going to pick up the larger features, but then they could see this small, it doesn't show up on the, with the sensor, but if it's this big, maybe it will. So maybe as long as you have a range, then you can be sure that they're definitely going to get something. They just might not get it.
And they can play around with other variables, like how close they want to hold the sensor. Maybe that will help them pick up more stuff. There's really a lot of things that they can.
So you mentioned variables.
Yeah.
That's a good thing. Oops, I just hit the mountain. Let me grab the sensing device. And as has been pointed out, depending on how much time you want to spend in class on this, I mean, literally you could spend a week and a half, depending on how much you, with the kind of details you wanted to focus on. I think, Elena, we talked yesterday about the amount of time that a teacher would spend on this, maybe in doing a lesson. Are we thinking 2 or 3 periods?
Yeah, I usually, for any kind of lab that I'm trying to do, and again, I'm at the high school level, so you middle school teachers might have a different opinion. But usually once a lab runs past 3 days, I've found that my students start to lose interest and want to move on. So
Okay.
I would suggest trying to keep it to like 3 days. Yeah.
So while it's fun for some to experiment with finding out how small an object they could pick up, what kind of resolution they get, the major goal is to demonstrate some model how sonar could be used to replicate radar. Okay. So we're going to collect some data here for you in a few minutes. Mariana mentioned variables. So think about some things that might come into play, things that you would want to control in taking your device, scanning the surface. And I want some feedback from the teachers. Put in comments. What kind of controls, what kind of variables would you want to control and maintain control over during the experiment? I'm interested. What do you got?
Oh, good.
Please answer in the chat.
So the idea is we're going to scan the surface. We're going to go one path at a time across the surface and record the data. What kind of variables are at stake? What kind of things do you want to control?
Speed of the movement,
Okay, good. Speed. So
keeping the scanner at the same height.
okay, how fast am I going to go? How high will I be? How do I maintain that height? We've got the string. Okay, what else? Speak to me.
Anybody else have ideas?
there are some practical aspects. The one thing I can tell you is the angle of view of the sensor.
The size of space you're sensing,
Okay,
lighting, using a grid pattern, maybe how many times you scan over the area.
okay, all good things. I'm interested with lighting.
Yeah.
Are we using light? Could we do this in the dark? Could we scan the surface of a planet in the dark? Do we need light? Mariana,
No.
you're the planetary
With
scientist.
this method, no, we don't, because we're using sonar or sound,
Okay,
so we don't need light for that. And also in a real world setting, the electromagnetic waves send from the probe, so we don't actually.
okay. I love that response, light. That's a good point of discussion. Love it. Okay, so some additional things to keep in mind. I mentioned we've got an angle of view here of about 15 degrees. Now, we talked yesterday that we could take a piece of cardboard and cut out a 50-degree angle and see, how much of the floor that would cover. Or we could just try it. And so I think we've decided, I put some, Bill, can you see these hash marks down here on the floor?
Yes.
Okay, so we've trial and error, Mariana and another student and I, excuse me, we worked tirelessly last year, trial after trial to see what worked and what didn't. We found that, now these are 12-inch squares on the floor. We tried creating a grid pattern all the way across, decided that was too much work. And so we decided just to try and put marks on the floor to decide where our scan would start. Now, here's where it's important to think about the number of students that you could have on a team. One student's going to operate the computer and hit stop and start on the software. One student's going to probably do a scan. One student probably needs to stand parallel to the direction of the scan. And from here, I can't tell which mark I'm on very easily. And so if I have a student over here, they could say a little to the left, a little to the right. I have a student monitoring perpendicular to me the speed that I'm going. And so there's all kinds of options for students to become involved. And so let's see, anything else? Mariana? Elena, that I overlooked?
The only thing I just thought of is kind of more of a caution is we have like tile floor in here, which reflects sound waves very nicely. But if you have like carpet in your classroom, did you guys test it on carpet?
We did, at one point, tested on carpet. The reflectivity so these are all reflective to sound, but to varying degrees. The cardboard is not going to be as reflective as the floor. So the material that your features are made of is going to make a difference.
So if you have access to a room that has tile, or like maybe students could do it in the hallway or something like that. If you find that trying to use the sensor on carpet isn't working so well, just keep that in mind.
Yeah, you won't get a smooth surface. So in the 3D image that you create, you need a good baseline. The reflective floor will give a good baseline. A hard surface gives a good baseline. Carpet won't. So, all right, I think we'd like to try and collect some data. Is that our next step?
Yeah.
Okay. I'm going to model this before we actually collect the data. Bill, I'm going to ask you to move your camera to this side over here. Okay, you don't need to show my face so much, but I'd like to see the sensor and the floor. Can we get that in?
Got it.
Okay. Now, I'd like to have Mariana stand over here. and tell me if I'm in line with one of my marks.
So right now you're close to in between the marks.
Okay,
So I would say a little bit more to the left.
okay, let's,
Yeah, that's perfect.
okay.
There.
Now, you notice I've got some marks on either side outside the box. There's a reason for that. There's, first of all, a little bit of a time delay from the time that the software operator hits start and the sensor starts to pick up the data. So I have to have some margin outside the box. And so I'm going to start with, think about it, if I've got a 15-degree angle hitting the floor, I don't want to be right over a surface feature to begin with. I'd like to be a little bit away so that I have a clean area around me. Keep in mind, if you've got students working in the same group or two groups in the same room, you don't want to pick up the next group. You also don't want to pick up your feet because doing this is going to help pick up your feet. Bill, question.
There was a comment, and I'm guarantee you guys thought about this at least a little bit. Would a PVC pipe stand that stretches across the field that you could slide the ruler and sensor across be helpful?
Yes, potentially. So another option to do this would be to have a PVC pipe with a student on one end and a student on the other end. That would be,
I think they're saying that it would slide on the PVC pipe. You would have that and just have like a stand with a PVC pipe running across it. And that way it's constant height as you go. Sure.
yeah, this is, pretty easy to maintain a height, but sure, that'd be fine as well.
Okay.
So you do pick up, and you're going to see from some sample data we've collected, you're going to pick up some noise, some anomalous data from reflections, something that's reflecting that you're not aware of. And so that could be your feet. So I don't really want to be like here. I want to be more like here, which is why I can't see which mark I'm over. Okay? So now on a tile floor where I see tiles, I can slide the string to kind of follow a line along the tile. Mariana, am I at the first mark?
Go a little bit to the right.
A little bit to your
Perfect.
right?
Perfect.
Okay. All right. So I'm ready to make the first scan. And nope, nobody's at the computer now, but I would tell my computer operator to hit start and we'd start scanning. So let's go ahead and Mariana, do you want to share your screen?
Yeah.
Okay. So Mariana's going to go to we're using Vernier Graphical Analysis to collect the data.
Which is free.
Which is free. Is it free?
Graphical analysis is yes.
Yes, okay.
And students can even have it if they have Chromebooks.
Correct.
Okay, so this is the software that we're going to be using. And so we're using the Vernier Graphical Analysis. And so first we want to be able to connect the actual sensor that we have. And so we'll click New Experiment here at the top left and Untitled. And so here, this is where we want to pick the right sensor. So we're going to go to Sensor Data Collection. And so it's going to pick up any devices that are on. Dave, is it on?
Shouldn't be.
So you'll just press a little button on the very front of the sensor and it will turn on. And so you can see here, it's picked up one of them. So for the kids, they'll have to make sure that they pick the right one. And so at the top or the front of the sensor, it tells you what ID number it is. So they'll just have to make sure they pick the right one. And so they'll click connect. And then it should say connected. And when you go with the sensor, you should hear a little clicking sound. Do you want to like bring it close?
Yeah, do you want to hear the clicking?
Yeah, bring it over here.
Okay.
And since you're so close, you can also see where the ID number is right there. Let me show that to them. So the ID number is right there.
Good.
Okay, are we good?
Yep.
So now once we've collected, we just want to change a few things just so it's easier for us and we get the data that we want to get. So we'll go here at the bottom left and we'll click on the mode. And so we want to change the rate to have 20 samples per second. You can switch it up between 10 to 20. It's all written in the lesson plan what we think is best, but you can go ahead and play around with it. And we want to make sure that it doesn't end automatically. And so we want to click manually for the end collection. That way it doesn't stop after 5 seconds and whoever's collecting the data can walk as slowly or as fast as they'd like to. And then we're ready to go. And so now when we want to start collecting the data, we'll click this collect button. And when we want to stop, we'll click this same button here that will say stop. And so now we can go ahead and collect data from Dave whenever you're ready.
Okay, so I'm going to wait for your signal. When you hit start, then I will start, because there's about a half-second delay.
Yeah.
Okay.
And you'll hear on the sensor, you heard a moment ago, it's kind of a slow clicking. Once Mariana hits collect, the sensor will start clicking a lot faster, and that's how you know that it's collecting data.
Okay, so I just figured out that I probably will do better walking forwards than backwards. So I'm going to go this way. And I'll get my feet out of the way. Mariana, I'm good when you are.
Okay, 3, 2, 1.
Okay,
All right. And something that might help the kids when they do this is to kind of say in their heads or out loud, 1 Mississippi, 2 Mississippi. That way they can just make sure that they're timing each run that they have at the same speed that they're doing. And so we can just see here in this data, we have a pretty much a constant level from the surface. So here on the y-axis is position. And so this basically means the distance from the sensor to whatever it's detecting. And so because Dave ran over something that had no surface, it was just the ground, we just have a constant height, which was about 1 meter. And then on the time is just the time since he started collecting. And so another thing that's important, just that's helpful, is over here on the top right, we have the view options. And so we can see for each run or each time I click collect, what we're getting with the sensor. And that way it's a good way to keep track of how many times we've passed it over. So we're going to do it again. And I'll just click the same collect button and Dave will just move over 1 spot and do the same data collection. So 3, 2, 1.
okay.
All right. And so then we can see here on the data set, we have data set 2. So we know that he's done 2 runs. And if it's not exactly the same amount of time, that's okay. That's something you can fix in Excel as well. Perfect. So we'll do another run. And so we can see here also the data shows something new here. But because he wasn't over a surface, again, it's constant at about 1 meter from the ground.
Is that the length of your string?
My string is actually 1.1 meters.
And you did the 1.1 because of the sensor, the depth of the sensor?
No, I did it just
For
because I
that.
liked 1.1.
Okay, all right.
It could be,
I thought maybe you were subtracting out the depth of the sensor, which would make it pretty close to 1. Go ahead and say that's what you did. Just say that's what you
I
did.
could say, yeah, I subtracted out this, it's 0.1 meter.
Okay.
I'm kidding. We've tried on actually from about 0.5 meters to 1.5 meters. 1.5 meters, we lose some resolution, but yeah, 0.5 meters, I think it was pretty good, 0.75 meters. Play around with it and see what works best for you with the scale of the features that you have.
In the lab, does it say 1.1?
No, it says, decide what you want to do.
Oh, okay.
Your choice.
Okay, fair enough.
Because all your kids will be different heights. So most naturally hold it wherever they naturally hold it. So it really doesn't matter how high your sensor is, as long as your sensor doesn't get like this close to your surface feed.
Yeah.
Then it doesn't pick up.
It creates garbage. Yeah.
Okay, we're gonna do 3 or 4 or 5 more scans and then show you what some data looks like. Mariana, are you
Yes.
good?
3, 2, 1.
Okay,
Okay, so when something like this happens, it's okay. It's just noise that's happening. So we had big spikes in the data. But we can see generally with this kind of section right here, you can see this is good data. It has a spike in it, but we can still see there was a dip, which means that Dave passed over a box. And it's kind of inverse of what you think for the kids. The distance decreases, the position decreases because the sensor is closer to whatever it's detecting. So that means it was a high object that decreased the distance to the sensor. And so Dave passed over a box and it was detected here in the data. But this stuff, if there's a big spike, it's usually just noise and that can be ignored later in the Excel data when you do the analysis. And then once he finished passing over the box, it went back to 1 meter. So that's kind of what that's showing.
so just to be clear, the higher the box, the shorter the distance.
Yeah.
Okay.
Yeah.
That's a little confusing. You have
Yeah.
to think in reverse. Okay.
Mhm.
The other thing I did is I'm picking up the pieces of tape as I go because I've already lost track of how many runs I've done.
Mhm.
And so if I pick up the tape or, have some way to keep track of which scan I'm on, it would be helpful. Okay, Elena, how do I look?
More this way.
A little more that way.
Hold on. Yeah, that's it.
Okay.
Okay.
All right. Elena or Mariana, I'm good with when you are.
Okay, 3, 2, 1.
Okay.
Okay, so this was a good run. There's a little bit of noise at the beginning. That's not important. But we can see there was one box that it wasn't too high because we can see, again, think of this kind of like the inverse. So if this graph was flipped upside down, this is kind of what the surface would look like. There's a short box here, and then you have a much taller one, decreasing the distance to your sensor. And then we went back to the ground at 1 meter. So this was a really good run.
But let me ask you, and I'm looking at that and I'm going, okay, so there's a short box, then there's a shorter box, and then a taller box. Okay, okay.
And you can kind of see in there what we were talking about earlier about resolution. Like if you're looking at the surface, right, there's space in between these boxes, but the sensor didn't pick up that space very easily. So you can kind of see the resolution there, which again is okay that it didn't pick up that space. That's a good point of discussion with the students.
Well, you can think about acoustics for a minute. We're using sound waves and we can't hear them. But when the sound waves hit that floor in those boxes, they're obviously bouncing back, reflecting off those surfaces. So, it's not surprising that we would not pick up that short distance.
Mhm.
Okay, let's do 2 more. Elena, am I matched up here to the next mark?
More that way. Yeah.
Okay,
Ready?
Brianna, ready when you are.
3, 2, 1.
Okay,
Okay, so this was a perfect run and we can see very clearly the data here, kind of modeling that. Yes.
now, I'm going to do 1 more, and I'm going to make a point, and that is, I'm reaching the end of my meter stick here, and keeping it level may be a little more of a problem. And if I were to go all the way across my surface, my arms won't be long enough. So what do?
Get a friend.
I could get a friend, yes.
Basketball player with long arms.
I could do that, or I could move over and go this way. So if I get to the other side of my surface, the other side of my terrain, and run out of arms, I can scan from the other side. Keep in mind, I want to go the same direction. I don't want to reverse directions. Okay, so Elena, I'm going to do this scan from this side. Tell me when I'm, and I don't really, I could have done it over there. I'm just making a point.
And that's also what the string is for. So if you do need to reach over and it's hard, you can look at the string and make sure that it actually is level.
Right.
Even though you are reaching.
And the reason I can adjust the string, I made the string adjustable, is because if the string is, it's going to hit a surface feature. And so I want to avoid that. So thinking, these are the kind of problem solving techniques that your students should be challenged with. And, you know, they're going to mess up. They can try it once. They learn and try it again. All right, let's do one more scan. And Elena, I'm going to ask you to tell me if I'm lined up.
Perfect.
Okay. Mariana, ready when you are.
3, 2, 1.
1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi. I'm all done.
All right, perfect.
Okay. Should we look at some data?
Yes.
Okay, I'll
So,
turn it over to you.
okay. So now we're just going to show you how you want to export this data so you can actually kind of manipulate it. And so you'll come over here to the, again, the untitled on the top left, and you're going to save as. Oh, export it. Okay. Ignore what I just said. You're going to export it. And you want to export it as a CSV. And this is really important because Excel won't take anything else, and we want to do the data analysis in Excel. And so we'll save a CSV. You'll save however you want to do it. Experiment.
Mariana,
Yes.
can I interrupt you for a minute?
Yes.
We're doing this in Excel, and I'd like to ask the teachers, who would use Excel and who would be restricted to using Google Sheets? Let's get a tally here.
Can you guys throw that in the chat? Let us know which would you be using, Excel or Google Sheets?
We're going to show you both ways.
One Google sheet. Sheets. They can do either, but they prefer sheets. So it looks like Google Sheets.
Okay, we'll run through it in Excel and then we'll do it in Google Sheets. The initial steps are going to be the same.
And they said, one person said, because their kids use Chromebooks. And I would assume a lot of schools have Chromebooks because they're cheap and easy to get and all that. So thank you for that knowledge.
Cool. So I think saved already. Yeah, so you'll just do that whole process, save it however you want, but you want to do it as CSV, which is what you use for sheets too, right?
Yeah, so, and also this would be a good part to mention for your students who only have access to Google Sheets or they have Chromebooks. When they save this file, it should go ahead and ask them, like it should pop up Google Drive for them to save the CSV file rather than like on a regular PC, it would save it to your file explorer, right? So the process here also shouldn't be that different for a PC versus a Chromebook for the students.
Cool. And so you'll save that, and then you can go to Excel or your sheets and you'll open it up. And so this is some data we've collected previously, but it's just the same process, same sort of thing. So you'll just go to File, Open, and then you'll kind of just pick the data that you saved.
I don't think they can see that
Oh,
at the moment. Or
Right.
if you have to share.
let me stop sharing and share again. Share.
Maybe.
Okay, sorry. So you'll go, like I said, this is some old data that we've collected in the past, but it's the same process to what we showed you. You'll just go to File, Open, and then they'll just open the data wherever they saved it. And then it should show them this. And so we come through the data, we see there's some differences here. The most important thing we want is to see what the data is. So here we have time, position. Oh, shoot. Okay, so It might be better to open. Let's see.
Maybe open.
No, it's not. 1 second. Let me see again.
The holdup is when you download or when you open the CSV file, it should have time, position, velocity, and acceleration
Right.
for every single data set that you gathered. But we only need time and position. So we wanted to show you how the CSV file should look unedited, essentially.
We just need the first time
Yes, you just
and
need
the
one
remaining
time
positions.
and then all of the position columns. So you would delete all of the other columns.
Okay, so I'll go back to sharing my screen. Share. Okay, so I'm just gonna open what we just did with Dave just to show that whole process. And so I did experiment, CSV. I'm just gonna open that. And so just to convert, just because it's a CSV to an Excel file, you just want to switch it over. And so this is what we mentioned before. We have time, you can see here at the top, and we have position, velocity, acceleration. And for each time, it should be exactly the same or generally. So you need to keep just one time data. You don't need to keep for all the other ones. And so this is something that you can have your kids just go and delete for each run. And so they can just delete that. They don't need it. They only need the time from their first run. And then we want to keep position. That's very important. But the velocity and acceleration, those are not needed. And so this, you can just have your kids delete this each time. And so they have to be very careful not to delete the position.
You want to delete the columns, right? So there's no space in
Right.
between them.
So the kids can also just, hold on. Delete. And then they can kind of make their data a bit neat.
So what you're telling me is they're getting rid of that. You just want the first time, and then you want the data set from each run. And that's it.
The position.
The position, sorry, the position data from each run,
Yes.
and delete everything else.
Yes. And so they can go through this process, kind of set it up however they want. But this is the most important part. You need your position in one time data set. And so then we'll go back to the other Excel that I was looking at. And so this is the data that we've cleaned up. Like I mentioned, we had the position for each of these data sets that we ran. And so we have time all the way up to 81. So we have here 3.95 seconds. So we're just going to maintain it for this. We're just going to use up until the time is done for each of the data sets. And so we're going to select the data that we want. The time ends here, so I'm going to just use this. And I'm just going to stretch it over until we don't have more data. Just like this. So we've selected all the data that we want. We're going to go to Insert, Chart, and then we want to use a surface chart if you're using Excel.
You want to show the calculation first,
Oh,
right?
yes. So, sorry, this you're going to do
Rewind.
after, yes, rewind. So what you want to do, and it's said in the lesson plan for the kids, they need to do a calculation to see the difference between the heights. So like when we calculated it in Vernier, collected the data, it was inverted, so we want to invert it back.
So when you say inverted, the data we recorded was the distance from the surface feature, the top of the surface feature, to the sensor. But if we want the height of the feature, we have to take that distance that we measured and subtract it from the length of the string, 1.1 in our case.
Yes.
Okay.
So I'm just going to clean this up. You can do the calculation easier. All right, so this is the data we collected with Dave. And so I'm just going to make a new one, call it height and new table. And so to do this, basically you want to do a calculation in Excel, but you want to know the height at which you held the sensor, which should be the same for each of your runs. And so Dave held it at about 1 meter. We'll just do 1.1 minus whatever we collected. And so we want to do that for the position. So we'll come over here to the first position data that we collected. We'll click on it and then just click enter. And so it calculated that for us. And then we just want to do this for each of the data sets. So we can just take this, pull it over 1, 2, 3, 4, 5, 6, 7 times. So 2, 3, 4, 5, 6, 7. And it's calculated it for each of the data sets that we collected.
And you did that by grabbing the bottom right
Yeah.
and had a plus sign and you just drag it.
Exactly. And so we want to do this for all the data below. So we'll just do that same process, just dragging downwards. Just do this. And it's collected it for us. And so when we don't have data here, it'll just 1.1 minus 0. So I'll just put 1.1. Okay, so this is the data that we actually want to be graphing now with the time at the beginning.
So you have another set of time in there. Did you see that?
I
Oh,
do. Thank you.
you have a time.
Yeah, so that's,
Yeah, that would mess up your,
yes, it would.
Yep.
Thank you.
Mhm.
So that's stuff that the kids will have to watch for,
Mhm.
because it is easy to miss that stuff. There we go. And they can count it. If they did 6 runs, they should have 6 position data, so they can check that kind of stuff. But this is what you'll actually need to be graphing with your time. And so now I can go back, right? I'm not.
Yes.
Anything else.
Now
Okay.
you can go
cool.
back and insert chart.
So we have the time. We did the calculation all here for all of this position data. I'm just gonna select it all here until we don't have any more time data. Let's just do it here. And then we'll go over here to insert, chart, and then surface, and we have a graph. Now this looks a little bit weird, and so we're going to fix it, but we have some sort of data. And so we're going to do select data here at the top in chart design. And we want the Y value. So this is going to vary a little bit whether you have Mac or PC, but it's going to be about the same. And so for Y values, we're just going, it just wants the title for some reason. And so we're going to just select the title so it knows what data it wants us to collect. And so we're just going to click that. Okay. And now it fixes your data, gets rid of that really big triangle we saw. And so now we can manipulate this data. These large spikes the kids can ignore, but they're just noise that when we collected the data, remember when we did it in Vernier, there were some big spikes. This is just showing that here. But now we can manipulate the data. So we can right click on the graph and we click 3D rotation. So this is how they're going to be able to see their graphs a little bit better. So with Y rotation, they can kind of turn the graph, see where those mountains are. X rotation, they can do the same sort of deal. And something that can help them kind of see the graph at different shapes. So if they go to depth, percent of base, they can switch this to whatever number they want. And the bigger the number, the better. And they can see a little bit more of a realistic surface. So everything's not so bunched together. But it really, they can play around with this. There's no correct answer. And then they can kind of turn their graph around, see what it looks like. Where here on a surface like this, would they like to land? Definitely not on a slope like this. They can think about stuff like that. But this is how you would do the data manipulation on Excel. So yes.
Okay, I'm going to be the slow learner because I followed you and I'm pretty good with Excel and all this. Start over again.
Okay.
So get rid of the chart or the table.
Okay. What's this? What's this?
Yeah.
From here.
Yep, start there. So you selected, and I'm looking at when you did that, I'm looking at T. Is there anything in T?
Oh, no, but it should ignore it on its own, even if you do select it.
Okay,
You can delete it to make it look neater, or
because I'm wondering if that was that. But anyway, I don't know. But okay, so will you delete that?
Yeah.
Just for me, just
yes.
being. Okay, so now you said you select down until the time runs out, right?
Yes.
And then you go over. Go ahead and go, yep. Well,
All the other data before, we want that, so we'll just collect it.
okay. So once you've done that, now you're going up to where again?
Insert here at
Okay.
the very top. Can you see that? Oh, they can. Okay.
Yep.
Kinda.
Yeah.
That's
so
fine.
just do insert your
Table
chart.
or chart.
Chart, and all the way at the bottom, you want surface,
Mhm.
Okay.
and that will give you this.
And then you just drag that to make it bigger.
Yeah,
Okay.
just drag it from the edges. And so we don't want this big triangle at the beginning. Oh, and just to clarify, each different color is a different run that you did. And so it's combining all of that data that you did horizontally. It's combining it all into one.
Oh, okay.
Yeah.
Okay. So now you want to get rid of that and you went in and you did what now again?
So we want to get rid of this big triangle. For some reason, we have to select the data here at the very top under chart design. You're going to go to Y values. You're going to delete this like that.
Okay.
And it wants you to tell it what data. So it wants the title of the data you're going to use. So you're going to select the first one, the time, and just move it all the way until you don't have any more data.
Okay. So you're just selecting row 1.
Yes, exactly.
Okay.
You're just going to select it and you're going to click OK. And then your triangle should disappear.
Okay.
And now you have something that's more workable.
And I remember you saying to ignore those spikes and explain to
Yeah.
the kids that's just background noise or something that happened. Okay.
And now we want to do the rotations, getting all of that. So you're going to right click on your graph and it should open this little window over here. You're going to click 3D rotation. And now you have all these options, but the most important ones are the XY rotation and your depth. And so XY is just going to rotate it so you can see it better however you'd like. And then the depth is what's going to allow you to change how it's stretched.
And you turned that to 1,000 last time, right?
Yeah, so the bigger, the better, the more realistic it is, but the kids can do it however they want. I mean, planetary surfaces are always different. But we did 1,000 and it stretched it out. And so they can see little hills, ridges, that kind of stuff. If we do 2,000, it'll stretch it even more. If we do 500, it just changes it how they want, however they'd like. And then this is kind of a surface that the kids can actually analyze and look at. Based off what they made on the ground over here, this is what's being shown on the graph.
So really they're looking at that point, they know what was on the ground.
Mhm.
So they're looking at this and saying, does this semi compare to what's on the ground?
And then based off this data, they can think about, like NASA scientists, where would it safely be okay to land a rover that's worth millions of dollars?
Mhm.
You don't want to land it on a slope because it could just fall over. It's not going to be stable. It would be maybe best at the top of this hill, maybe below the hill, stuff like that they can consider. Would their rover have wheels to be able to get over that hill? This is all stuff NASA scientists think about, which they can think about for their planetary terrain as well.
Mhm.
So,
Okay.
yeah.
Another thing that they think about a lot with rovers is where could I land my rover so that I might find evidence of life? So I know, remember which rover, probably Perseverance.
Yeah,
Yeah.
the latest one.
They wanted to land it inside of a basin because that basin had filled up with water at some point and had a lot of sediment in there. So they would rather land somewhere that was low lying where there was a high likelihood of water being there as opposed to somewhere up higher where it would have been less likely for there to be life at that location.
Yeah.
So usually when you're talking about Mars and rovers where they want to be landed, it's like we're looking for life
Yeah.
on those planets.
Yeah, and again, they can think about what kind of data they want to collect, what they specifically want to research. So they could be searching for life, so they want to look for water. But if they want to study the clouds, it'd be best for them to go somewhere higher. It really just depends on what they're interested in to study, or maybe they can hit multiple of those. So like having a rover with wheels or including a little helicopter that can fly, this kind of stuff. There's really no limits to what they can think about. So yes. Cool.
So hopefully I'm doing the right segue question. So clearly most of these teachers are going to be using sheets.
Yes.
So how is this different?
Okay.
I'll stop sharing.
So Downloading, like opening the file in Google Sheets and editing it so that you have just the data that you need is pretty much exactly the same. So Google Sheets and Excel work almost exactly the same. The only difference is when it comes to graphing, Google Sheets does not have a surface chart option. So what we're going to do instead, let's see. Yeah, okay. Yes. We're instead going to use a online tool called Chart Studio from the website Plotly. And this is linked in that addendum document. It looks like this. If you can see that, it is one of the documents that was shared with you or is linked on the website where they access this material.
It wasn't shared with you initially, but it's on the website where you guys, and I can resend that back out. I'll put it in the chat here in a second. Good.
Yeah. So the kids would have downloaded the data set from Graphical Analysis and saved it to their Google Drive. So they should save it somewhere where they will remember where it is located. And you see, I have two versions here. One is a Google Sheets file already. The other one was saved as an Excel sheet from Graphical Analysis. So if I open that one, what the kids will see is it looks similar, more similar to Excel, but they don't have nearly as many options to edit this document. So to convert this to a Google Sheet file, just go to File, Save as Google Sheets, and it'll convert it. Okay, so now I'm working with a Google Sheets file. And just like before, you can see there's that data here that I would need to delete. So I can scroll over, scroll down, and delete all of that and get rid of that data because we're not going to graph it. So that's kind of opposite of what Mariana showed. So I'm just deleting the data instead of highlighting the data.
And when they calculate for the position, like doing that 1 point something minus, is it all the same?
Is exactly the same.
Okay.
Yeah. So calculating the height, say I want to do that right here. The only thing that's a little bit different is you might have to, Google Sheets ends at Z because it's like, oh my gosh, you really want to analyze that much data in Google Sheets. But you can insert more columns to the right, insert columns to the right, and just keep adding columns, however many you need. But yeah, that calculation is exactly the same. So it equals type 1.1 minus, and then go to your first position, hit enter. And then even the like mechanics of it is the same. You hover over this little dot in the bottom right corner and your cursor turns into a plus sign. And then you drag it to the right, however many times you need to, and then leave it highlighted and drag it down however many times you need to. So that process works exactly the same as what Mariana showed you. Then once you are done and you have done all of your calculations, you'll want to save it again as a CSV file again. Because it converted it to a Google Sheets file, you need to convert it back to a CSV file. So you will do File, Download. CSV stands for comma separated values. I learned that yesterday. And then, so that's now saved in my downloads. I'll keep that there. For the students, it again would have them save it in their Google Drive somewhere. So they'll save it in their Google Drive. And then in Plotly, this link is in that addendum that either has been or will be shared with you.
It has been. I put the link in the chat.
Okay.
And then you can scroll down under remote sensing and it says addendum. So you can click on that.
Sweet. So this website is free for you and your students to use. You just have to make an account. And there's Plotly and then there's Plotly Chart Studio. You want Chart Studio. So you can see my URL up here is chartstudio.plotly.com. And then I would like to create a chart. Okay. And then this I actually think is a little easier than trying to graph the surface in Excel. So you just import your data in the top right. You can either upload the file or, as you probably know, with Google Documents, you can share via URL. So you can also put your URL link here for a Google Sheet if that is easier for the students. So I'll just upload from my downloads here, which I actually want to do my fully edited one from yesterday. Double check. Yeah, so you can see here I have all of my height calculations to the right here. And then to create my chart, I just go to Trace, plus Trace. And then I want this to be a surface chart. So I'll click on, do that one more time, under Type, where it's automatically chooses Scatter by default. I'd rather it be a surface chart. So there's some 3D chart options down here. And I want 3D surface. Click that. And then I like how simple this looks. I just need to choose the X, Y, and Z data that it's going to graph. For the X data, I want my time column. So I'll just click that for my time data. I played around with this a little bit and turns out you actually don't want any Y data, but you do want Z data, and your Z data is all of your heights. So you'll have to go in, drop down. This is the only little tedious part, but you can kind of see your surface form as you go. So you add in each of your heights.
And there's not like a control button that you can hold and click multiple? Not that you saw. I think that's,
Yeah, it just.
because actually when you do it, it's pulling it out.
Mm-hmm.
Oh, that's interesting.
So you just do it however many times. And I could keep going forever. Let's do 10, because I have 19. Okay. Now, what I like about this is that rather than having to like change the degree of rotation in Excel, you can just click and drag this around, move it around to see what the surface looks like. So again, this spike right here is just noise for this data set.
So you can flip that all the way around?
Mm-hmm. I can turn it
Oh,
this way. I can look underneath, look on top.
And I think with Excel, you can't do a full,
Yeah. So
this is pretty nice.
yeah. And I thought, especially for middle school students, entering the data on this left-hand panel looks to be a little easier.
Mhm.
Okay. So yeah. Trying to think if there's anything else. That's all I got for the Google Sheets version.
Well, let's pause there just for a second. If teachers, if you have any questions about what you just saw, that we can maybe go back and clarify. And clearly, if you have a question, you know other teachers are going to have questions as well. So if there's any questions about what you just saw right now, go ahead and put it in the chat and we'll see what we can do to answer them. So this is either a sign that the two of you did really well of explaining, or they are so confused that there's no questions. Either way.
Please clarify.
Does each student have to make an account in Chart Studio?
But wait,
Yes.
what was the
I
question?
believe so.
Does-
Does each student have to make an account in Chart Studio?
Yeah, so this, if you have your students in groups, just one student in the group would need to do it. But if you want each student to have a graph or make their own graph, then yes, every student would need to make their own account. Mhm.
Will the video be on the website of this lab? They would need to go back and organize the data to look back at the video, so.
This video that this professional development, this webinar will be on that same link that I sent you, underneath the remote sensing, at some point, probably before Friday. So if you need to go back and watch this again, you can.
And in these slides, the ones that.
Louder. Louder.
Sorry.
Sorry.
The slides from the very beginning that we used, there's a link for a video of just the exact process of how we did everything today. It's with Excel, but this video shows.
So we're gonna share that link, that PowerPoint on that same page?
Yeah.
Okay. So by Friday, if I have available of it, I'll have it linked back up.
Anyone is also free to contact me, Dave Cedarberg, and I can pass your questions along to Mariana or Elena, either one.
They said, thanks.
We
So-
have 5 slides.
We have just a wrap up couple slides that we'll jump to.
Hold on. The image of this is flipped from the one in Excel. Is that because you flipped it?
The one,
The one you were doing had
Yeah.
the spike went down versus her spike went up.
yeah, let me share I think, what happened was on Excel, you look back at your Excel file, I think you did graph the position rather than the heights. So yours, I think might be upside down.
Okay, so yeah, so
Yeah.
I graphed the unedited, that wasn't calculated, but you'd have to do, so yeah, it would be flipped upside down.
Yeah, so the one that we showed you in Excel, looks like we accidentally graphed the position rather than the height. So the original data that we got from graphical analysis, whereas the one that we showed you in Plotly was the calculated heights, so it is flipped upside down, yes. So you would want the flipped ones.
Right. And then, so that answered that question, yes. It might be interesting it might be interesting to ask students what a crater would look like and why our model can't show that.
Yeah.
I'm just gonna throw my 2 cents in. When I taught middle school, I would have probably done this very simple, like you guys did first, but then I would have allowed kids who, like David was talking about, who are intrigued, and I would have given them the opportunity to do this, if they get done with other stuff and they want to go back and try, maybe not doing as many runs, but doing it where the things are closer, or even draping a fabric over it or whatever, right? Give them that full freedom and flexibility to see what happens and then before they do it, what do you think is going to happen?
We have, in the last couple of slides, we've got some images and video of kids actually doing this, bringing in some crazy materials.
Perfect.
Stop sharing, page it over to you.
Okay, so on that same slides that we started at the beginning, towards the end, we have some other things, some more discussion questions for the students. So what the greatest challenges they had, how could they improve the accuracy, efficiency, all that kind of stuff. And what kind of feature they tried to create. So if they tried to make a crater, did it actually show up like a crater? And so if with the data that they collected, we asked them if they think they'd confidently be able to actually land a rover there, or if they'd actually need more information. And so then we just had the groups present to the class, and we just told them we wanted to see an image and we wanted them to name the surface they decided to make. And they just presented that to class so we could see all the different things that were created and how efficient they were able to graph it. And so these are some pictures and a video from Columbia when we implemented this in the classroom. And so we had kids that took a box, you can see like in the video, they made a pyramid, like a mountain. They took, in the bottom left-hand picture, they took petals from a flower. They made pyramids with cups, and they made like a little tunnel with a box. And so these are that we really didn't expect the kids to go this into depth, but when they start to think about it and what is out there, they made the coolest surfaces ever. Which some things could be resolved, some not, but that's stuff that they learn as well. So yeah, so this was a good experience for the kids in Columbia. And so this is just some more information and lessons. We have Teachers for SMAP, which has some lessons and resources, which Dave, you can talk about more if you'd like. And then we have just the YouTube channel with other lessons that the kids, from Saturday morning astrophysics that Dave hosts as well, that these kinds of lessons, as well as the website for the kids to sign up if they'd like, and more information can be found there as well. So, there's a question.
Yep. The question is, what would the actual job title or education major needed for someone that does this for NASA?
So there's a lot of things. So with these rovers, what's cool is that you need people from so many different types of disciplines. So it could be someone like me, like a planetary scientist or an astronomer. We need engineers to help actually build these things, and like what kind of wheels would you like, what's best across these surfaces. You need chemical engineers. You need everything you can, social media managers to help promote these types of things, get funding. So really almost any field you need someone. So it's open to any kind of interest to any student. So yeah, but if they wanted to do specifically the research, doing this kind of modeling, the more likely types of majors would be like planetary science, some type of engineering. So, but yeah.
Let's all gather around our tree.
You want to see you or the terrain?
A
little bit of both.
See both, sure. No, just what I just wanted to have us on camera. Are there any more questions, Bill, for us?
Not at the moment.
Okay. We can wrap up anytime, but I'm happy to hang out for some questions. If anybody has a question.
Well, don't wrap up yet. I still have a couple things I need to tell them. So when you're done, I still got a couple things. So don't leave yet. Okay.
Do you want to be on camera, Bill?
No, I don't need to be on camera, what I'm going to do.
Okay, so we can turn it back to you. I just wanted to thank all the teachers for being here, and thank Elena and Mary for their parts. And I hope you have fun doing this lesson. We're here for questions if you have them. So, thank you.
Thank you.
Any questions at all before I let them go, and not let them go, but have me take over? They said, thank you.
All right, Bill, take over.
No questions, I said.
Okay.
Another thank you. Okay. I'm gonna do two things. Actually, I'm gonna do three things. First thing I'm gonna do is I'm gonna give you my email, and my email is in case you need PGP points, the professional growth points, or whatever they call them in your state. What you'll do is you'll just send me an email. It can, the title or whatever for the email can be remote sensing, or you can put the date, whatever. I know who you are because I have your names from joining. On the document that I use, I put the last four of your social security number on it. That way the people know that I actually had contact with you, because how else would I get the last four of your social? Do not put in the email, here's the last four digits of my social security number. Just put in those four numbers and I will add that to the document and I will send it back to you. If you don't want to do that, I fully understand. I will fill out the document without the last four, and then it's kind of with you and your state whether or not they accept that or not. It will say Purdue University, it will have my name, it'll have contact stuff. So for the most part, a lot of you have been coming to each session, so you kind of know the drill. But if you're new to this, that's how you get your PGP points. And I give 4 hours. I figure you're going to be here for almost 2, and you're probably going to mess around with 2 hours trying to figure out what the heck happened, right? Okay. That's the first thing. All right. Second thing, I am going to give you a link to a Google form. And give me a second. Kathleen, you are fast. She's already emailed me.
Gotta get those PGP.
You got to get those PGP points. Okay, so there's the link to the Google form. This Google form is a simple form. It's a little hoop for you to have to jump through, but it is a form that will allow you to get possibly, and I use the word possibly, some of the motion sensors. We have money because we have an awesome alumni who has donated money so that we can run these middle school professional development. And we are able to send certain number of sensors out based off of the amount of money we have and the number of people who have come to our professional developments. So if you would like to get one of those or a couple of those sensors, fill out that form. I've been telling everybody towards the end of July, we'll make kind of a decision on how many people have asked for things and how much money we have, and then we will start sending that stuff out. I will be shipping it straight to you. Whatever address you give me, that's where it'll go. And it even says shipping address. So make sure that you are putting an address that you can have something shipped to you. And it'll be shipped straight from the company, not from Purdue University. So you'll be getting those straight from Vernier when they get shipped to you. I hope that was clear.
So would you say like go ahead and ask for 6 if I want a class set?
Ask for what you want. You don't always get what you want,
Right.
but sometimes you get what you need, right? Okay. No, so just, yeah, ask for what you feel, but based off of the numbers and what we have, we'll adjust accordingly. Okay. The last thing, if you haven't, and I put it in there earlier, make sure that you go back to the page that we sent out earlier that has all the information for each of the professional development. And I just put that in there again. And you can scroll down and all the documents that they were talking about, they're on there so that you can scroll and look and see that. And if you missed one of the other sessions, you can click where it says click here to access this recorded session, and you can watch that session from before. If they have documents for the lessons, they're on there as well. So like for the remote sensing, you've got the remote sensing mapping terrains. That's the main lesson. The mapping terrains addendum is there. And then the remote sensing itinerary was what we did today. And there are links off of those for other things that you might find of interest. Okay. Those were the 3 things I wanted to make sure that everybody received. Any questions? No questions. You guys are awesome.